Hi guys. So today we're going to be looking at DFS, depth first search, which is a graph traversal algorithm and graph theory. So we're going to go over the theory first, and then we're going to look at code implementation in the next video. Now, remember guys, this theory stuff, it's important, okay? Like, I know a lot of people jump right into this code, but understanding the theory thing allows you to properly be able to apply these to the appropriate problem. You really, some of it, you don't need to know, and that's what this is, right? So this, in my opinion, what I'm going to be going through here, these are the aspects of the algorithm that I think you should know, that I would expect, someone that I'm interviewing to know, etc. All right, and so if you have any questions about any of the theoretical stuff, hit me up, help each other out in the comments. I'll be looking at the comments, answering questions there as I can. So and then a lot of this stuff I try very hard. I always do the implementation first, which is based on simplicity, ease of debugging, and reasoning about, and these lessons are meant to kind of follow along with that code, right? So that I can kind of relate the two back to each other. Okay, so let's get to it. Okay, so first, a little analogy. So if you want to, this is kind of like imagine you being in a maze, and it's basically, the idea is you pick one path, you go all the way to the end before you turn around and come back. Okay, so it's a systematic way of exploring graphs or trees, and you visit all nodes in a depth-oriented fashion, because there's also BFS, breadth first search, which kind of, it's more, think of it as in layers, where you kind of analyze, you analyze a matrix sort of by its rows, and we'll get to that in a minute. Okay, so it's a graph traversal algorithm, and it's used in like pathfinding, connectivity checking, and topological sorting. Right, so game logic, like mazes, that kind of thing. This is what this it's used for that. Social networks, you probably that's where you hear most about this, is like in social networks. People are represented as a node, nodes and stuff like that. All right, so let's get to the key concepts. So remember guys, these are key concepts in my opinion. These are things that I find important. So so a graph consists of verts and edges, right? And the edges are the connection between the vertices. And graphs can be directed or undirected, right? Depending on whether the edges have a direction. Okay, so you have directed graphs. These are like a one-way street in a city, or a prerequisite for a task, right? Where you have A to get to C, or well, in this situation, right? So you got A. And then let's say to get to D, well, you got to do a pit stop at B, right? You can't skip B, right? So that would be the example of like, a directed graph. Now, undirected graphs, man, I did not edit this. So undirected graphs. So these have a two-way relationship, like friends, right? So think about social networks, right? So when you make a friend, right, when you add someone to your friends list, well, it's a two-way relationship. You're their friend, they're accepting to be your friend, and and therefore they are also your friend. You're both friends, right? So it's a two-way relationship. And then you've got weighted and unweighted graphs, and this depends on if the edges have weights, right? And so you've got direction, if the edges have direction, and if the edges have weight. Okay, so weighted edges have associated weights, unweighted edges, the edges don't, right? So you can imagine this, weighted graphs, imagine shortest path algorithms, right? And I actually kind of have it called out down here, Dijkstra, Bellman, Ford. So think about it, right? So if you've got, think about a delivery driver. So if you're, got this thing too. All right, so imagine that you're a delivery driver, okay? And when you wake up in the morning, the company knows your route, they know where you got to go, they know your packages, all that stuff, right? So And so what they do is, so you want to direct the driver down the right path, right? So if you have a driver that can get to node D, and so say that, we have node D that the driver has to get to. Well, we don't want them to take A, B, and C. We don't want them to go A, B, C. We want them to go A, B, E, F, right? So less abstractly, we don't want them to go to first and make a right and then make a left on Derby, right? We don't want them to do that. We want them to go straight, make a left, and then make a right onto second, right? That's what we want them to do. And so, you would has, traffic conditions, traffic conditions worsened or were relieved, et cetera, you could push more weights to these individual paths and they would be prioritized, right? If that makes sense. And then, you got unweighted, which is basic relationships, right? I mean, unweighted, there's no, it's just, you're related in some way. And so, like I said, weighted graphs are using shortest path algorithms, and unweighted graphs, just determining if there's a connection, basic relationships, things like that. Here's a table. I'll let you guys scan over to see some, the various combinations of the two and the problem domains. Now, graph representations, right? So these are the way that these graphs are represented in memory. Now, we're talking about the graph. This isn't the algorithm, right? We're talking about the actual graph here, right? So the actual graph that the algorithm will traverse. Okay, so the way that these graphs are represented in memory is pretty important. Okay, so in the code that I've written, that I'm going to be, guiding you through, we're using adjacency lists. So these adjacency lists, it's a map. It's a map from a node to a list of its neighbors. Very typical tree situation, right? So like right here, right? So you got A is connected to B, A is also connected to C, and then B, D, E, right? So how you would really see a tree, right? Typical tree. And so that's an adjacency list, okay? And these, you're going to see these a lot more out and about, right? Because they're much more space efficient. We'll talk about some big O in a minute. And then they're just, the graphs that you see out in the world are typically sparse, and are typically sparse. Okay. Now you have adjacency matrices, right? So these are 2D arrays, right? They indicate edges or a lack thereof, right? And so these are used less, but they're used in very specific domains all the time, right? So these are when you have very dense graphs, right? So imagine image processing, scientific simulation, and game development, right? Where you have very complex relationships, and there's a lot of those. A lot of those relationships, right? Where so that's what they're used for, in those certain situations. But and definitely. Learn about those. I will have code up on my GitHub showing an implementation of those. I will do a video at some point going through those. But my main thing right now in terms of the videos that I'm posting is really those foundational things. But I'm also going to do some system design stuff and things like that, and some other topics, more advanced topics. And so I'll definitely eventually get to doing something with adjacency matrices. Okay. So now adjacency lists, I'm going to go into those because that's what we're going to be using. Okay. And so that's going to be the representation we're going to use. So this is how you would see it in your mind, right? This is a typical tree. This is how you would envision it as a human being. Now, laid out in memory, it would look like this, right? Where you have A connected to B and C, right? A is connected to B and C. And then you have B connected to A, D, and E. And then you got C connected to A. And then you have then you have D connected to B, and then E is connected to B. All right, so this is what it would look like in memory. Okay. Now, here's some big O if you're interested in this. This is good to know. The big O stuff, whatever, but you should know. You need to know when and how. You need to know when and why to use these things. Okay, so you'll see here. this stuff can be boring to a lot of people, so I'll let you kind of go through this. You have an adjacency list. Here's your space complexity. You can see that the adjacency list is linear space with respect to the number of vertices and edges. Each vertex stored once, and each edge is represented once in the list, right? In an adjacency matrix, everything is stored, regardless of whether an edge or not exists. And so, yeah, they get very, they're heavy. And then, neighbor traversal, efficient, slower, linear. Both of these are linear, but this one is so the thing about neighbor traversal and a matrix, that's where you have to look an entire row. That's what I was talking about earlier on about the layers. You got to traverse basically each row, right? And that can take time, especially if it's not a very dense graph. It's just a complete waste, Edge existence. It's easier to check for edge existence in matrices. It's a 2D array. You get that immediate lookup. Think about it. The underlying array, the underlying data structure is an array. So all of the stuff that you benefit from using an array, you're going to benefit from this, right? Or from the matrix. Okay. Okay. And so now let's get into this. I want to get into this right quick, right? And kind of talk about traversal and the way that these are populated. Okay. So the way that these are traversed is that you start at a chosen node, right? So let's say that you start at A. And so the idea is to visit a neighbor and move deeper until all the neighbors are explored or you reach a dead end, right? And then you backtrack to explore the remaining nodes, okay? And so as you visit these nodes, they're going to be in a stack, okay? They're built up in a stack, and then there's going to be storage for your visited nodes, right? And so I'm going to walk through what the stack is going to look like, and also what your visited collection is going to look like, right? So what's going to happen is you're going to visit A, right? To start off, you're going to be visiting A. Your stack is going to contain A, and visit is going to contain A. All right. So let's say that you want to move on to B. Okay. So you're going to move to B. The stack is going to be A and B, and then visited is going to be A and B. So now do you want to go to E or D? Well, let's go to D. So the stack is going to have A, B, D, and then your visited is also going to be A, B, D. Now we have to backtrack to B because we're at a dead end, right? D is not connected to E. So to get to E, we have to go back to B. Okay? So now we're going to go back. So now D is popped off of our stack, and visited now contains A, B, D. Okay? Now the stack, we're going from B, we can get to E. So the stack is now A, B, E. Visited is A, B, D, E. Okay. Now we have to backtrack to A because we need to get to C pretty much, right? So now we have to backtrack to A because we're at a dead end and all the nodes in the branch have been visited. So we go down the other array. So we go to A to C, and then from C to F, right? And so we go all the way down till we get to the end, then we go back up, and then we're like, wait a minute, this is connected to a neighbor that hasn't been visited yet. So we go down here, and it's like, okay, nowhere to go. So it's like, we got to go back up. Okay, well, we're at B. We're at B now. We're back at B. Where did we go back to B? We went back to B right here. Okay, well, we know A has been visited, and D has been visited, but there is a connection to E, so we need to go there, right? And so we go down to E, and then same thing, nowhere to go. We go back up to B, check its neighbors. It's visited everything. Then we have to go back to A, check its neighbors. Well, it hasn't been to C, right? So pretty simple, right? Pretty easy to understand. Now, how is the graph populated? Okay, so this is important too. Okay, so the values in an adjacency list are based on some value that is compared to the root. Now, okay, this is going to be very important to remember in the code, especially if you're not used to reasoning about these things in a certain way. And also there's a bit of recursion that's in the code, and we'll really narrow down on this, right, about this whole idea of comparing to the root. Okay, so values in adjacency list are based on some value that's compared to the root. So this could be as simple as comparing the size of integers, which is what our example is going to do, to comparing the relation to someone in your social network. Now this is a great example, right? So imagine that you have a social network where you have your users have feeds, right? And this feed contains updates from your friend list, people on your friends list posting things. And so imagine that you want, relatives of your users you want their post to have priority in users' feed, right? So what you would do when a user goes and adds a friend, a new node, if that node is a relative, it will appear at a higher level in the tree, and it will have more priority when it comes to how that feed is processed and displayed to the other user. All right. All right. Cool. I think that's good for now. I think that's enough theory. Like I said, if you have any questions about this stuff, hit me up. Help each other out in the comments. Remember, be cool. Don't be an asshole. Ask respectable questions if you want respectable answers. And we'll see you in the implementation.